All right, let's jump right into this explainer. Imagine the ultimate nightmare scenario for an electric vehicle. You've got a massive, high-voltage battery system, literally packing enough energy to power a house for days, and suddenly it goes completely blind to its own internal heat. We are talking about a totally blind battery management system, or BMS, and honestly, that is a straight, terrifying path to thermal runaway.
So, what actually happens when an EV battery goes numb like this? Well, to understand how automotive engineers prevent catastrophic battery fires, we have to look really closely at the microscopic components that act as the battery's nervous system. Because simply put, if the system can't feel the heat, it absolutely cannot fight the heat.
And that brings us to the real hero of our story here, the NTC, or negative temperature coefficient thermistor. These are incredibly tiny, highly specialized sensing components where the electrical resistance actually drops as the temperature goes up. They are the absolute first indicator of battery safety, the primary gauge for what's happening electrochemically inside the cells. But if just one of these little sensors breaks down, a section of that massive battery goes totally numb. And having a numb spot in a system powerful enough to blast you down the highway, yeah, that's not something you want.
To tackle this, we're going to unpack a really brilliant 5-layer safety hierarchy today. First, root cause analysis. Second, hardware and software diagnostics. Third, design prevention. Fourth, manufacturing control. And finally, production validation.
Starting with Section 1, root cause analysis, tackling the core reasons behind sensor failure.
Let's meet the villains of our story, the physical, chemical, and mechanical threats trying to knock these vital sensors offline. There are 3 main diagnostic trouble codes, or DTCs, we have to watch out for. First is P0A9D. This is a hardware short circuit that drops the voltage to near zero. It usually happens if the sensor wires get mechanically crushed or if the insulation is literally torn open by heavy, high-voltage bus bars rubbing against it. Next is P0A9E, an open circuit that spikes the voltage over 4.8 volts. You'll see this when extreme thermal stress cracks the epoxy casing, or when crazy chassis vibrations actually pull the connector pins right out of their sockets. And finally, P0A9C. This one is a sneaky performance drift. It happens when moisture leaks in, creating weird parasitic resistance, or when the thermal glue ages and the sensor just falls off. When it detaches, it's just measuring the cool air in the gap, completely missing the fact that the battery cell right next to it might literally be boiling.
Moving right along to Section 2, hardware and software diagnostics.
So how does the BMS fight back when one of those physical failures actually happens? Well, the hardware relies on a deceptively simple but incredibly crucial circuit. The BMS uses a highly precise 10 kilo-ohm pull-up resistor paired with the NTC to create a voltage divider. This feeds the raw analog voltage data into an ADC, an analog-to-digital converter chip. From there, the software takes over, using the B-parameter equation or a Steinhardt-Hart lookup table to translate that raw voltage into real-time, ultra-accurate temperature data.
But what if that raw data is corrupted by one of the failures we just talked about? Engineers actually hard-coded voltage boundaries as the very first line of defense. If the voltage drops below 0.2 volts, signaling a short circuit, the system instantly ignores the mathematically impossible high temperature it calculates, say something crazy like 150 degrees Celsius. This stops a false fire alarm that might shut off your car while you're driving on the highway. On the flip side, if the voltage spikes above 4.8 volts, signaling an open circuit, the system completely rejects the fake reading of like negative 40 degrees. Why? Because if the system genuinely thinks the battery is freezing solid, it will crank up the internal PTC heaters to warm it up. And doing that could actually roast a perfectly healthy battery right into thermal runaway.
So the software is smart enough to ignore impossible physical data, right? But it doesn't just sit there, it actively responds. It constantly monitors the rate of temperature change, hunting for impossible jumps, like a 50-degree spike in a single second. It also cross-checks temperatures with neighboring sensors. If one sensor goes rogue, the system instantly kicks into a limp home mode. It substitutes the highest adjacent temperature reading just to be safe, immediately forces all the cooling water pumps and fans to 100% max capacity, and drastically cuts driving power. And most importantly, it permanently prohibits DC fast charging. This guarantees that those internal blind spots aren't pushed to the point of catching fire.
Let's jump to Section 3, DFME design prevention.
Now, how do we stop these failures from happening in the first place? In the engineering design phase, preventing this specific failure carries a top severity rating of 8 or 9 out of 10. Engineers tackle this by totally upgrading the raw materials. They specify AEC-200 automotive-grade sensors that are built to survive extreme thermal shock. Instead of bulky, messy wiring harnesses, they use flexible printed circuits, or FPCs, packed with underfill glue to absorb all that mechanical vibration. They also strictly route these delicate low-voltage lines in dedicated, dual-insulated channels, keeping them miles away from those heavy, crushing high-voltage bus bars. Plus, they use advanced computational fluid dynamics (CFD) simulations to perfectly position these probes at the exact extreme hot and cold spots of the battery pack.
And honestly, you have to appreciate this massive physical design upgrade. The old vulnerability was relying entirely on thermal adhesive, which is basically just high-tech glue. The problem is, over years of heat cycles, that glue ages, expands, and eventually shears right off, leaving the sensor dangling there measuring empty air. The new standard? They added a simple stainless steel spring clip. This clip applies constant, relentless mechanical pressure to ensure the probe permanently touches the battery cell. It completely eliminates the terrifying risk of a sensor falling off while the battery secretly overheats behind its back.
Which brings us to Section 4, P0A9 manufacturing control.
Because let's face it, even the most brilliant designs can fail if they're put together poorly on the factory floor, so strict process controls are locked in. Manufacturers use statistical process control, think of it as a relentless digital auditor, to monitor the exact volume and mixture ratio of the thermal glue. They bring in high-precision multi-axis robots for stacking the battery modules, just because human hands might accidentally pull or pinch a delicate wire at a sharp angle. To fight our old enemy, moisture, 100% of the circuit boards undergo vacuum-conformal coating. This essentially seals them in a protective force field to physically block water drops and prevent electrical leaks. Finally, at the end of the line, they hit every single sensor with dynamic high-load pulse testing to verify its thermal response speed. They want absolutely zero lag before that battery is allowed to leave the factory. And finally, Section 5, DVP&R Production Validation.
Before a single car design is approved to hit the road, the whole system has to survive a brutal gauntlet of testing. And in this phase, speed is literally everything. Engineers will intentionally inject short and open circuits right into a running system. The BMS software has an incredibly tight window. It must accurately detect the fault within 500 milliseconds, substitute a safe temperature value, and force those cooling fans to 100% capacity in under 2 seconds flat. You get less than 2 seconds to prevent a total disaster.
Then, the physical torture begins. Components are literally strapped to a 3D random vibration shaker for 300 hours, just violently vibrating back and forth. And while they're shaking, they are getting blasted with wild temperature swings from -40°C all the way up to 85°C. Through all of this insane abuse, the electrical resistance jitter has to stay under a microscopic 0.05 ohms. That proves the soldering and the epoxy won't crack under the stress of a real-world driving lifespan. Remember that sneaky moisture problem we talked about earlier? They test for that with an absolutely grueling 500-hour test at 85°C and 95% relative humidity. They literally drip coolant on the components while applying a live voltage bias. It's an extreme electrochemical migration test, and it proves that the vacuum coating perfectly prevents any electrical leakage or the growth of dangerous metallic dendrites between the little pins. And just to be absolutely 100% certain, on the actual assembly line, every single sensor connector undergoes a physical pull test. A machine yanks on the wire with at least 80 newtons of force. This guarantees that those tiny connector pins are seated so securely that they will never, ever vibrate loose, no matter how bumpy the road gets.
So, the overarching takeaway from all these engineering documents boils down to this quote: temperature really is the first indicator of intrinsic thermal runaway safety. What looks like a super simple thermometer on the surface is actually backed by this massive, invisible ecosystem of mechanical design, super advanced software algorithms, robotic manufacturing, and just brutal physical validation testing. And every single piece of that puzzle exists purely to keep those tiny sensors reporting the absolute truth.
Which leaves me with a question for you. The next time you plug an EV into a high-powered fast charger and you're pouring immense energy into those battery cells, are you going to think differently about the microscopic, 5-layered safety net that is working overtime behind the scenes just to keep you safe? It's pretty wild to think about. Thanks for joining me for this explainer. The engineering protecting us is truly profound when you peel back the layers. Keep learning, and I'll catch you on the next one.